Hi, my name is Matthew Schlew, and I'll be presenting my semester project for Computer Engineering 537, Automated Wireless Attacks with the Raspberry Pi. So I've had a Raspberry Pi for a while, and I've been able to, I didn't really come up with any good projects or uses for it. So I thought this class would be a great opportunity for me to, try something new with the Raspberry Pi, you know, put it to some good use and try learning some new wireless attack vectors that I feel haven't been tried before. So the basis of my project is to take a lot of common wireless attacks you see, such as packet harvesting, deauthentication. If you've heard of the new cookie cacher program developed by Matt Sullivan, take a lot of these different attack vectors and automate them into a small Raspberry Pi device that won't take any interaction upon the user's part to be able to run. So just a quick overview of Wi-Fi 101 for maybe non-technical users that are watching this video. So Wi-Fi signals are frequencies being broadcast through the air, similar to the way radio is. And due to the fact they're broadcast this way, it gives us the opportunity to perform a lot of the attacks and makes a lot of the attacks feasible in this project. So as you can see, you have different wireless channels, 1, 2, 3, 4, and on up. And for example, channel 1 is up 2.412 gigahertz, and as you go away from the channel, it gets the signal gets weaker. And the same happens for on channel 6 and 11. You can see you have a lot of different channels in here you can choose between. And so one of the reasons I bring this up as well is because if you look at the current landscape of wireless signals, there's a lot of saturation with wireless traffic out there. This is a spectrum analysis of the Wi-Fi in my apartment alone. You can see it's pretty crowded. There's a lot of wireless devices transmitting data, and that translates into a lot of opportunities to capture data and to perform attacks against this wireless traffic being transmitted. So, you can imagine if this is just my apartment building, if we move to somewhere like the library during dead week or finals week, or a cafe on a busy weekend, those are a lot of places that there's going to be even more wireless traffic flying around, and there might not necessarily be as much encryption or levels of protection as you might see common in a lot of home wireless devices. So first off, we'll talk a little bit about the Raspberry Pi. So the Raspberry Pi is a small computing device. It has 500 megabytes of RAM, and it's very low CPU power. It doesn't consume a lot of volts or milliamps of power. You can insert a small SD card over here to run your operating system. You have a couple peripheral interface devices such as USB, LAN devices, HDMI video. It's about the size of a credit card with a cut in, a couple of these slots extend up off it and make it just slightly bigger. So the cool thing about this, though, is that makes this project really unique is that a lot of these attacks that other people have been talking about in papers during this semester, or that we've heard the teacher lecture about in class, they're performed from laptops with add-on wireless cards and things like that. You have to run virtual machines possibly, or boot into Linux. And a lot of these things, are bulky and they're not discrete. If I'm walking through a library or a cafe, I'm only going to be there for 5 minutes trying to just capture data. It looks pretty weird if I just have a big wireless card sticking out the side of my laptop and I'm walking through a cafe, trying to steal people's data. So, the idea behind this project is if I can take a small Linux computer, create a program that's going to automate these attacks, and then be able to take that computer, put it in my pocket, attach a custom-made power supply to it, I can walk into a cafe or a library or a Starbucks, and these attacks are running from my pocket while I'm ordering my coffee. I'm capturing people's wireless data, and it will help people make people aware of some of the attack vectors that are out there, and it's a good wireless security auditing tool. So you as a system admin would know just exactly what your business is transmitting through the airwaves unencrypted. So this is the Raspberry Pi booting up for the first time here. I was installing an operating system on it and imaging the SD card. As you can see here is the keyboard and the different peripherals plugged into it. So before I got too into the programming and trying to get the software running onto it, I wanted to make sure I could get a battery pack that was going to provide enough power to maybe say get around about an hour of battery life, and to run this computer from your backpack or something like that. So I started out by making a battery pack that would run this Raspberry Pi. So as you can see right here, this is a phone charger. It uses a little micro USB cord that just, right here it's just plugged into a wall charger. So I want to be able to take that and instead use a battery pack. So the first thing I did was construct a battery pack for the device. So I took these plans and they were slightly modified from a device called a Minty Boost. There's plans from an electrical engineer made and posted online for a device that can be used to charge your cell phone. Now the only difference between charging your cell phone and using this to run the Raspberry Pi is it needs to be run a little bit more efficient. If you have a significant change in voltage, if it drops up and down a little bit more, it's not really going to be that big of a deal for your cell phone. It stops charging for a second and starts charging again. But hooking this into a mini Linux computer, if the power is fluctuating, I found that the CPU on the device tends to freak out and do hectic things. So if the power flow wasn't steady, the CPU would kernel panic and the device would shut down to protect itself. So I could have run out and got a bulky cell phone charger off Amazon or something like that, but I thought it'd be more unique to make a very small pocket-sized charger that fits into a Altoids can and can power the Raspberry Pi. So as you can see, this is the size of this is a 2 AA battery pack, and the breadboard that powers this all is about half the length of the battery pack. So you can tell that this is a pretty small device here. So this is soldering some of the capacitors and resistors onto the board, and here you can see we have the boost regulator on there, and all the other parts soldered in there with the positive and negative leads. So after I finished getting this put together, I had some help from the electronics shop in Vancouver and from one of my friends that's an electrical engineer to make sure this was working properly. We went ahead and tested the power supply just to make sure it wasn't going to damage the Raspberry Pi and it was outputting the steady volts and correct volts the way we wanted it to. And not being too great at soldering, I was lucky I only had to clean up a couple things. I only had to resolder a very small number of parts to get it working exactly the way we wanted it and getting it to output a very steady voltage. And so after I got the this little tiny power supply that would fit in my pocket next to the Raspberry Pi, the next thing I want to do was get right to work on the software for this project. Let's make sure we can get a lot of these scripts running that are going to be powered by the device. So the next thing I did was set up move my development environment for my laptop onto GitHub. So if you're not familiar with GitHub, it's a version control system that you can use it's perfect for projects like this where you want to program in a more distributed type of environment and control the versions of the scripts you have floating around out there. So using GitHub allowed me develop on my MacBook, develop on a Fedora and Debian testing environments, and make small bug fixes, push them up to my GitHub account, and then later on I could pull them down in my Raspberry Pi and test them and see if they were working. And some of the interesting parts I found with this was when I was testing in the Fedora and Debian environments on either servers or virtual machines, the x86 instruction set worked pretty well at manipulating the hardware to put it in the correct states that I needed to run a lot of these attacks, whether it's deauthentication or packet harvesting, or even trying to just simply open up a reverse shell. A lot of times you want to change the MAC addresses of the devices that you're running on the network to stay anonymous, or you want to set your wireless card into promiscuous mode or monitor mode so you can capture all the traffic you see around nearby. So that was pretty easy to do on an x86 instruction set. There were a lot of the libraries that were needed to do that were readily available. Now I ran into some issues originally when trying to port a lot of these to the ARM architecture. A lot of the Aircrack suite and a lot of the tools like that do this for you. The libraries weren't very stable and wouldn't work all the time with all the chipsets that I needed to that I was using for this project. So I bought about 2 or 3 wireless cards to test with the Raspberry Pi, and a lot of these chipsets originally didn't work the way I intended to or weren't working consistently. So luckily though, about halfway through the project, the Backtrack Linux team released a new operating system called Kali Linux, which had ran natively on the ARM architecture, and it had a lot of these software packages on the Raspberry Pi that I could use, incorporate into my program to make it run more smoothly. So that was a big relief, halfway through the project to have something great to happen like that and to help me get past a lot of the obstacles that I ran into in this project. And so other than using that for a development environment, I also did issue and bug tracking in a ticketing system. So there's a great company called Atlassian that makes a program called Jira, which is a ticketing system that can be used to pretty much track almost any IT project. It's pretty flexible in creating a workflow that'll work for your project at hand. So anytime I thought of an idea I wanted to add to the project, like for example, like logging originally, I hadn't thought of creating any logs of attacks that happened and whether they were successful or not. And so that was kind of an afterthought. As soon as that popped in my head, I added it to Jira. I programmed on it on my laptop. I pushed the changes up to GitHub. I pulled them down to the Raspberry Pi and tested them and got them working. So it was really, using a ticketing, setting up a ticketing system along with a GitHub account to test this really helped me keep track of my project. It helped me focus on the goals and things I wanted to accomplish and really move those along in a timely manner throughout the semester. So this is, the ticketing system that I used. This is a screenshot of the ticketing system I can use. In the past, week or two, it shows the open and resolved issues that I was working through. It's a good example of, just a lot of the tickets I was opening and closing as I worked on this project. So we've talked a lot about the battery packs and how I developed the program and all that. So now it's I'll show you some of the attacks that I was able to set up with this, and we'll talk about some of the cool results I got and some of the things that other problems I ran into when working on this project. So the first thing you do when you run the Wireless Pi program is you boot up the Raspberry Pi into your operating system, and as you can see here, for the initial part, you can plug it into anything. You're going to need a display and a keyboard for this. And when you're actually running the attacks, you don't, the battery pack isn't powerful enough to power the display for this. I found, the HDMI and the video out is one of the most power-intensive things the Raspberry Pi can do. So you actually need to plug it into a wall socket when you're initially setting up the attacks. And the first thing you'll see is the Wireless Pi menu, and it gives you the automated attacks. And so far, I've programmed about 3 attacks into the system. So we have deauthentication, packet harvesting, cookie cacher. It automates the caching of data process, and this is just phoning home. So it looks for open wireless networks around you. It connects to them. It can talk back to a central server that you specify, and it pretty much opens up a reverse shell into your Raspberry Pi. So it allows you to walk into a network and let someone remotely log into your device and perform a lot more interactive attacks while it's just sitting in your pocket. So as you see the sign says right here, these attacks will run upon restarting the device. So what you would do when it's plugged in here, select one of these attacks, power your device off, you take your battery pack, you walk into the place that you want to perform the attack in. So for example, one time I tried packet harvesting in the library. So I walked in, plugged the power supply in, just shoved it in my book bag, walked around the library for a couple minutes, and all the while the device in the background, is booting up. It's manipulating the hardware to put it into a monitor mode. It's running part of the aircrack program to collect data. It's changing its MAC address ahead of time to make sure nothing is recognizing it on the network, and then storing this data. It's using a primary WLAN 0 interface to store this data, and on a second wireless interface that's plugged into it, it's phoning home and relaying this harvested data back to a central server. So it's pretty cool to know that after this attack setup, I walk around and all this is happening for me. So first we'll just go over briefly what the Wi-Fi deauthentication attack was here. So deauthentication is there are disassociation or deauthentication frames that terminate a session between a client and an access point. So my device specifically looks for heavy wireless traffic in the area. So if it sees, like, for example, the IA state access points receiving a lot of traffic, it's going to see a really strong signal from that and a lot of traffic going back and forth. So it'll start sending deauthentication packets out to that network and disconnecting a lot of the clients it finds associated with that specific SSID. And it'll then go ahead and log the data about the clients that it was de-authenticating during that attack. So one of the most important things, as I mentioned briefly earlier, is the logging capabilities that were built in later. So you have this device in your pocket and it's running, but you don't necessarily know whether it was successful or not. Was it actually de-authenticating people on the network? Was it having issues and wasn't able to run properly? Did the battery pack run out of data and nothing happened? So I went back later and put a lot of logging into more logging into the system. And this is one of the screenshots from the early functionalities that I had here. So for the de-authentication script, it's changing the MAC address to something random on a certain, and it specifies the date and time, and then next thing you know, you can see that it starts a pseudo interface called mon0 that it uses to send out the de-authentication frames across the network, and it's logging the date and time that it does that. And you can also see down here that this is indicative of the cookie cache attack. It denotes that wireless data was being transmitted back to a central MySQL database at 5.1 at a specified time. So that pretty much means that the device booted up, and on a primary wireless interface, it was collecting data with cookie cache, and on a secondary wireless interface, it was transmitting this data back to a MySQL database through an open access point it found. So a lot of times if you're able to find an open access point to relay the data back from the Raspberry Pi, my program will try to get the data out of the Pi as quick as it can, if possible. If not, it'll go ahead and just store that data locally, and you can pull it off your device later and analyze it with various programs that we'll talk about in a bit. And so as you can see, when walking through the library, this traffic was late. It was transmitted back into a MySQL database, and there were a lot of people in there during Dead Week, so it picked up a lot of MAC addresses, a lot of traffic very quickly. So it's pretty cool to see this work and to see successfully automate the capturing of session data and cookie data, out of thin air, pretty much. And one of the things I do want to quickly note, if I go back a little bit here, I had a friend who was helping me test the program, ask, what's the difference between packet harvesting and caching data? They seem both pretty similar. They're both grabbing packets out of the air and storing them on your Raspberry Pi or on a remote system. So I found that when I first started using the cache data process that it was pretty CPU intensive. It's Java running a program that's also connecting to a SQL database and trying to do real-time analysis of data that's inside the packets, and pulling out the significant data and parsing it out into the different database tables for that session data. And I found that the packet harvesting is simply taking wireless traffic found in the air and dumping into a PCAP file. So it's not doing, it doesn't, just taking that packet and saving it to a file is a lot less CPU intensive than actually trying to manipulate and look through that data. So I added just an attack vector, just taking that data and dumping it into a PCAP. And a PCAP is just a packet capture of the wireless traffic on the network. And so with that PCAP data, I was able to use, I could take that back and load it onto my laptop and load it into cookie cache, and I could see session data that was captured into that PCAP. Or I could go ahead and use a program like DriftNet and pull JPEGs or PNGs or other pictures out of that. There's also programs like TCP Replay out there. I can take the PCAP that I captured in the library and replay specific TCP streams back into a network with that device. So, capturing a lot of this unauthenticated data, you can see there's a lot of room for working with that data at a later time. If you can just pull it out of the air, save it, and get it to a system where you can do, further analysis on it. So, after going through this, I decided to come up with a couple mitigation techniques, and, this may not be complete. There may be more ways or better ways of doing this, but I thought, a lot of these are a good start to working with this. So, if you're setting up your own access point at home, you might want to consider using a hidden SSID, just not broadcasting that this is home wireless 1 or something. If you only have a certain number of clients connecting, you don't have a lot of guests coming and going from your network, there's, you don't really need to worry about broadcasting your SSID out there. Also, along with, hiding your SSID, you're going to want to add some type of encryption. So even if someone is out there sniffing packets on the network, all they're going to be doing is sniffing encrypted packets. And something at and if you have something like Iowa State's network where you need we have a lot of people coming and going, and a lot of people that need to connect to your network, even if you have a WPA2 encryption, everybody knows the password. That's still going to be helping to stop programs like mine or others from sniffing unencrypted traffic. So if you have a network called iState and the password for WP2 is iState, it doesn't matter if everybody knows that password because each individual frame is still being encrypted with the WPA2 protocol. So it's still going to give you a layer of defense in there. Another one more typical, if you do have to use open access points, consider MAC address filtering, or using things like 8021X or Radius. A lot of those will provide authentication on a network as well. So if you're a client side now, you don't have access, you don't have control of the access point. You're on campus in a library. You need to do some research, things like that. You need internet, and you pretty much are forced into using an open access point. You can use things like VPN to maybe there's a lot of VPN services out there where you can send encrypted data at a different layer in the OSI model back to a server that's wired into a network. You can also use SSH tunnels. There's a lot of good tutorials out there that show you how to use an SSH tunnel to proxy your web traffic through a secure tunnel, and also browsing the web with HTTPS. So if we are using an open access point, maybe we're not getting that layer of AES encryption at the physical layer or at layer 1 and 2, but even if we go down to the application layer on the OSI model, we can encrypt the contents of our web request, which is going to provide us a layer of security and stop people from looking at session data and plain text passwords that are floating across the network. So again, to kind of wrap up the project here, you have a large room full of people all using wireless devices, and the goal of this project was to take a lot of bulky equipment like this, like a laptop running the aircrack suite and capturing packets, and here we have sending deauthentication frames and all that. You want to take a lot of this bulky equipment that looks suspicious in a room like this and put it into a small Raspberry Pi like this that fits in your pocket and nobody can notice is running these same exact attacks. So overall, I had a lot of fun doing this project. You're trying a new attack vector and on a new system that hasn't been necessarily tested to work this way before. So I had a lot of fun working on it, and I learned a lot about wireless technologies in the process. So I think the project was a great success, and I look forward to adding more features to that attack list in the future, and opening that GitHub repository to be open source for everybody to grab a copy of the project if they want to work with it too. So if you have any questions, you can email me at shlu@istate.edu, or when I'm working on projects like this, a lot of times I'm tweeting out about soldering in the lab or frustrations from programming lines of code and things like that. So you can follow me on Twitter at mshlu, and thanks for watching.